Hey everyone, welcome to today's lecture. Today what we're going to talk about is distributed loads. To give you an overview of the lecture content, we're going to answer the question, what is a distributed load? And after doing a brief intro of that, we'll talk about some real-world applications of the concept, and we'll do some practice problems related to ENES 102. So let's get started really quick in introducing distributed loads by asking you a question. Take everything you've learned from the class thus far, and look at this good old-fashioned box. I want you to draw the force of gravity acting on this box and see what you come up with. I'll give you just a second. Alright, if you took out a pen and paper and drew your box, and then you drew the force of gravity acting on it, chances are you probably drew something that looked like this. You drew mg acting in the center mass of the box pointing straight down. Technically speaking, that's correct. But guess what? That's not true. That's not what actually is happening. In reality, our box doesn't just have a force of gravity acting in one place. That box is made up of millions, billions, trillions of atoms. And each and every single one of those atoms is being pulled towards the center of the Earth due to gravity. So realistically, to draw a true free body diagram of the situation, you'd have to draw the force of gravity for every single particle in that box. And by the time you'd finish, it would be a billion years from now. So we can't do that. In reality, what's happening is that the box has, as I'm saying, lots of arrows drawn over it. Now, you don't have to draw a free body diagram for every single atom. That would take far too long. But the picture to the right is technically a more accurate way of representing what the box is. The box, in theory, as it rests on the ground, every piece of that box is pushing on the ground at that particular spot. This is what we call a distributed load. And while technically the one on the right, captures the idea that more of the box is acting on the ground, the truth of the matter is, mathematically speaking, the left picture and the right picture are exactly the same. Which is why, when you drew the picture on the left, technically you're right, but what you're doing is a simplification of the true real-world system. So the first type of distributed load we'll look at in this class is called a rectangular distributed load. Now, why is it called that? Well, if you remember your shapes from kindergarten, it's because we've got a rectangle right there. And the way that a distributed load works is that it has the units of force per length, and it's distributed over some length, L. Now, what I was just explaining to you a second ago is that you can represent a distributed load, it's a rectangle, the same way you show the picture to the right. You can replace that distributed load with a single point force acting in the center of mass of the distributed load. So we usually call that the force equivalent. And effectively, because we have a rectangular load, the force equivalent will act in the center of that equivalent load, which in this case is L over 2. It acts in the center of mass, and the force equivalent is equal to the area of our rectangle, which is the base times the height, which is going to be the base, which is the length, times the height, which is the force over length. What you see happens is that the lengths cancel and you're left with just force. So distributed load is force per length distributed over some length. To find the equivalent load that you put in the middle of a rectangular load, you multiply those two things together and find the area of your rectangle. Let's take a minute and do an example. What I want you to do is pause your video real fast and look at the following example. We've got a 10 kilonewton per meter distributed load applied to this beam as is shown below. What I want you to do is calculate what is the magnitude of the equivalent force applied over that distributed load. So pause your video, take a second, and calculate that right now. After you've had a second to work on this, let's look at how you'd approach the answer. We just said that the force equivalent is going to be equal to the area of the rectangle, which is going to be the base times the height. In this particular case, the height is 10 kilonewtons per meter, and the base is 3 meters long. Multiplying those two things together, we get 30 kilonewtons. Now what I want you to do is if we replace that 30 kilonewton force onto the beam, where would we put it? pause your video for a second and figure out how far from the left edge of the beam would we put that force on our free body diagram. We see that we have 1 meter to the distributed load, and then the load itself is 3 meters wide. So we're going to get a value of 1 plus 3 over 2, which if we go back to our solution over here, we get 1 plus 3 over 2. This tells us that our distributed load will be located 2.5 meters from the left edge of the beam. There you go. Now, there's also triangular distributed loads that we have to look at and understand. Pretty much everything remains the same. We've still got a force per unit length is going to be the height of our distributed load, and it's still distributed over some length L. The difference with the triangular load is that instead of being flat all the way across, the force diminishes over a period of time. So what we actually get is, just like we did with the rectangle, to solve for the equivalent force of a triangle, it's going to be the area of the triangle. And the way that we can show that is with this picture right here. We can see that the force equivalent Fe is going to be equal to 1/2 the length times the force over the length, which is the area of our triangle. The other thing we can see is where the force is going to be applied. Now the center of mass of a triangle is actually 1/3 the distance away from the tallest edge. So in this particular case, if the base of our triangle was L, then our distributed load will be applied at L over 3 from the left edge. Now, let's work on an example one of these to see if you've learned the concept. We've got a 5 kilonewton per meter triangular distributed load shown on this beam right here, which is a total length of 8 meters. What I want you to do is pause your video for a second and calculate what the equivalent load is and where it's going to be acting. I'll give you a second to work on that right now. To calculate the equivalent load of the triangular distributed load, we find the area of the triangle. In this particular case, 1/2 the base times the height. That's going to get us 1/2 times 4 times 5. That gives us a value of 10 kilonewtons. And where is that going to be acting at on the particular beam we have here? Well, it's going to be 1/3 of the length, which is 4. So it's going to be located at 4/3 meters from the left edge of the beam. Now, what do you do when you have something that looks like this? We've got a more tricky example where we've got 2 triangles. Well, I think everyone's gut instinct would be to say, all right, I've got 2 triangles, so I'm going to treat this as if I've got 2 triangular distributed loads. So I'm going to have a distributed load right here, equivalent, and I'm going to have another distributed load right here, equivalent. That's technically true, but you're kind of making your life a little more difficult. And the reason is because if you look at this system, it's actually symmetrical. The triangle's on the left is balanced perfectly by the triangle on the right. So what's actually going to happen is that you really only need one distributed load in the middle for both of them. So that's just kind of a tricky example where you've got 2 triangular distributed loads, but you can actually make your life easier by combining them together using the principle of symmetry and applying just one equivalent load directly in the middle. Now, another thing that we need to look at is not only can you have multiple triangular distributed loads on a problem at the same time, but you can also have what's called a combination distributed load, which is both a rectangle and a triangle at the same time. On the right, in this example, we can see that we've got a rectangular distributed load with a load intensity, force per length of W2. On the left side, we see that something is different. Now, we call the one on the left a trapezoidal distributed load. And at first, you might be wondering how you deal with that. Did we learn that yet? Well, the answer is yes, you technically have. The way that you treat the one on the left is you treat it as though it's both a rectangle and a triangular distributed load. And the way that you'll do this is essentially using this method, which I'll show you right now. We take the trapezoidal distributed load and we break it into a rectangular load and a triangular load. The rectangular load, we say, has a height of F2 over L, and we say that that distributes over the entire width of our distributed load. The triangular load, we'll say has a height of F1 over L, and that's from the very bottom to the very top. Now, the load intensity of the triangle is going to be a little trickier, because in order to isolate that, what we'll actually have to do is subtract out the F2 over L, which you can see happening right here. So for the triangular distributed load, what we can see is going to happen is that we're still calculating the area of the triangle to calculate the force equivalent. But what we're doing now is we're not using the total height, F1 over L. We're using only the height from here to here, because that is the height of the triangle. It's F1 over L minus F2 over L. And when we look for the rectangle, we can see that the rectangle is just going to be the height F2 over L, because that is the height of our rectangle right there. So again, we just use the exact same positioning. The F of the rectangle will be directly in the middle at L over 2, and the F of the triangle will be located at 1/3 of L from the left edge of the beam, or from the tall end of the triangle. So whenever you've got a trapezoidal distributed load, don't panic, you're going to be all right. It just is a little bit more work, but you split it up into a rectangle and a triangle, and you tackle the problem in parts. What I want you to do now is just think of some real-world examples of distributed loads in your everyday life. Take a minute, pause your video, let the little question mark spin, and just think about, what are examples of distributed loads? What would one be? Where could that be? And to give you a hint, I've got one shown in the picture on this slide. So take a minute, pause, and think about what are some examples in your house or in your everyday life that are a distributed load. Okay, maybe you've come up with some examples, but I'll show you some of the examples that I've thought of. First one that comes to mind is this idea of, distributed load as being a pressure. Right now we're just looking at it in terms of its force per length. But realistically, objects aren't just two-dimensional, right? They're 3D. So a distributed load in reality is more like a pressure. It's a force divided by an area, not just a length. And a great example of that is everybody's favorite physics demo, which is when you have a teacher lay on a bed of nails. Now, actually, back in the day when I was a TA at Berkeley, I had the physics professor ask me to come to a room full of 300 or 400 people. He put a cinder block on his chest while he was laying on a bed of nails, and he asked me to hit the cinder block with a giant sledgehammer. We'd never practiced this before, and he was just laying on the thing, closing his eyes, holding a cinder block. And I went up in front of the class, and I was like, should he not make it, or should he make it? And let's just say the teacher survived at the end, and it was pretty cool. But the idea is, when you lay on one nail, it's ouch. But if you lay on a bunch of nails, you're distributing the force over a greater amount of area, and you end up being okay. Another example you can think of for distributed loads is snow loads, especially for those of us that live on the East Coast. Now, if you look at this example here, which roof would be better to hold the snow? Would it be the one on the left or the one on the right? Well, the one on the left, all of the force is going to be putting itself right directly onto the roof. Whereas the one on the right, you're actually, because the roof is sloped, one, the snow is more likely to fall off, but two, you're only actually having to fight back with the roof with the force of mg cosine theta. Now, the snow is really the example here as to what is a distributed load. The snow's weight is distributed over an area. Sometimes it's even, sometimes it's not, but that's a good example. And a little fun fact for you, when you walk by buildings with sloped roofs, especially on University of Maryland's campus, you'll oftentimes see these things up in the top right corner here. Now, what are those? Those actually are meant to help save lives. If we got a really big snowstorm and a lot of snow had kind of gathered on the roof, if it were to all fall down suddenly onto somebody 5-6 stories down, they'd splat for sure. But what these do is they're meant to break up the snow so that not one huge piece can fall off, but that smaller pieces fall off if they fall off at all. Another good example of distributed load in the real world is dams. Dams are a great example of distributed loads. Sorry for how bad that joke was. But dams are a really good example because dams are holding back large reservoirs of water. Here we have a picture of the Hoover Dam, which if you ever have the chance to go, very cool, much larger in person than you actually think it will be. But if you go and you look, what the dam is doing is it's supporting a giant amount of water behind it. And we know that as you go deeper and deeper in a body of water, pressure increases. Well, you represent pressure in fluid mechanics and fluid dynamics with distributed loads because the deeper you go, the more pressure you face. And actually, you can turn that into a statics problem, which helps you determine, based on the height of the water behind you, what load is applied to the wall. And using simple moment calculations, you can figure out how much essentially back area you need to prevent the dam from falling over altogether. So that is an example of a distributed load problem as well. And as I was saying, pressure increases with depth. So that's a good example of a triangle distributed load in the real world. Another good example is soccer. Now, I was a pretty terrible soccer player back in the day. I actually once kicked the ball up really, really high, and I wanted to head it, and I thought that heading it just meant you put your head directly under the ball. So I went and found the ball and let the ball just land directly on the top of my head, and I proceeded to black out, which I woke up a little while later, it's totally fine, and that's made me into the man I am today. But we all know in soccer, you want to wear shin guards, because if you ever forgot them, you were pretty upset. The reason is because if someone kicks your shin, that freaking really hurts. And a shin guard, the idea is to take that big force, which would be concentrated in a little tiny area, and distribute it over a larger area. Because by doing that, you're actually turning a big force into a bunch of little forces. So it actually helps keep people safe and players away from injuries. Let's now do some practice problems related to distributed loads so you can see how we apply these concepts to problems in ENES 102. Let's first look at this example problem right here, where we've got a pin at A, a roller at B, an applied load P, and a distributed load. I'll switch to a picture of my hand and show you how to solve this problem. Let's look at a distributed loads practice problem. What we can see right here is the problem asks us to solve for the reactions at points A and point B. We can see that we've got a beam, there's a pin support at A, an applied load P, 1.5 meters from the left, and a distributed load with an intensity of W, which is 9 kilonewtons per meter, applied over the last 3 meters of the beam. We can also see that at point B, we have a roller. So, just like every other statics problem, our first step is to draw a free body diagram of the system, and I'll do that down below. So, as you can see, I've got my free body diagram. I've got AX and AY for the pin. I've got the applied load P. I've got the distributed load W, and I've got BY. I've also drawn my XY axis. Usually our first step would be to do some of the forces in the X and the Y direction, and possibly some of the moments to solve. But because we have this distributed load, I would like to say that the first step is usually to replace this distributed load with its equivalent force. Now, the way to do that is to say the force equivalent for our rectangular distributed load is going to be equal to W, which is 9 kilonewtons per meter, times the distance it acts over, which is 3 meters. This tells us that our equivalent load is going to be 27 kilonewtons. As you can see that the meters will cancel out. So what you see is that we've got a force over a distance times a distance. And that's what a distributed load is. So now our equivalent load is 27 kilonewtons, and I'll draw that on our picture over here in purple. So we've got our F equivalent of the rectangle here, 27 kilonewtons, acting 1.5 meters from the middle of the beam. And the reason we know that it acts there is because it's a rectangle. It acts in the center of mass of that rectangle, which we know that the center of a rectangle is always right in the middle. And I'll even just draw that up here so it's extra clear where this equivalent F of the rectangle is acting. Now that we've done that, we can solve the rest of the question, and it actually becomes pretty straightforward. So we'll do some of the forces in the x direction. We'll set that equal to 0, and we have an AX, and nothing else. Because that's the case, we have nothing to balance out the AX force, therefore this is going to be equal to 0. Woohoo! That's easy. Now we do the sum of the forces in the y. Set that equal to 0. That's going to be equal to AY minus P minus 27 kilonewtons plus BY. We know what P is. P is 13, so I'll just rewrite this equation so that it's AY minus 13 minus 27 plus BY. Now looking at this equation right here, we don't know AY and we don't know BY. And again, like I've said in other problems, we could have realized right away we were going to have to do a sum of the moments equation because we have one reaction at the roller and two reactions at the pin. That is 3 unknowns. 3 unknowns is going to require us to do 3 equations, so we have to do sum of the moments. And usually it's smart to do it about the pin, just in case there was an AX. In this case, it doesn't really matter, but we'll just do sum of the moments about point A. Set that equal to 0. That's going to be equal to P times 1.5. So we get negative 13 times 1.5. You can see that this would cause things to go clockwise. So if I had my beam and I applied P to it, you see it's a clockwise rotation. So I put it clockwise, make sure that that term's negative, we're all good there. Now I have the 27 kilonewtons, and that's going to be 4.5 away. And that force would also rotate things clockwise. So we're going to have minus 27 times 4.5. And then last, we're going to have BY pointing up times a distance of 6, because we've got the beam is 6 meters long. And that would cause things to rotate counterclockwise. So say that's positive. I apologize for my terrible sound effects. Just trying to make it a little bit more interesting, but we got plus BY times 6. And now you can see that we have only one unknown in this equation. Now we can solve. We're happy, feeling good. So when we solve this equation right here, we will find that BY is equal to 23.5 kilonewtons. Now what we do after we've solved for that is we'll take that right there and we'll plug it back into the equation above, right here. And once we do that, that will tell us we've got 23.5 minus 27 minus 13. That's going to tell us that AY is equal to 16.5 kilonewtons. And there we go. That's how you do it. Fairly straightforward problem. Just a little bit of a review of 2D rigid body equilibrium with a distributed load thrown in. All right, now let's look at this problem here. It's a great bit more complicated than the last one, but it's still just using the principles of distributed loads. So let me switch to a handwritten solution and show you how it's done. Now let's look at this problem here. You can see that it's quite a bit more difficult than the first distributed loads problem we did. We've got a triangular distributed load over here. It almost looks like it's trapezoidal, but because we're not given intensity over at the right end, we're meant to assume that this is 0 over there. So in my PowerPoint drawing, this is actually meant to be a triangle, but again, it's a little tricky to get it perfect. What we can see is we've got 100 kilonewtons per meter applied over here. We've got a pin reaction at A, and we've got a cable up here at point B. Now, we're also told that we've got theta 1 and theta 2. and we know the distances of the beams, 4 and 4. And given the thetas, 1, 60 degrees, and theta 2, 55 degrees, we need to find for the reaction forces at point A and the tension in the cable, which is basically just tension B. So, first step, like always, draw a good old FBD, flipped free body diagram. So I'm going to do that right now. Okay, I've now drawn the free body diagram except for one thing, which is the distributed load. So my first step is going to be to find the F equivalent of the triangular distributed load. We know that that's going to be the area of the triangle, which in our case is going to be equal to 100 kilonewtons per meter, the height, times the base, which is 4 meters, times 1/2. So we've got the height, base, 1/2. So the F equivalent of our triangle is going to be 100 times 4 is 400, divided by 2, 200. So F equivalent of our triangle is 200 kilonewtons. So we'll draw that on our free body diagram now. And the question is, where is it going to act? Well, it always acts 1/3 the distance from the bottom. So it's going to act about here. And this distance here is 4/3 meters away. So I'll draw that on our free body diagram down here as well. And we'll label the force with 200 kilonewtons. Last but not least, I just need to include the dimensions on this. We know that the bottom beam is 4 meters, and we know that this section right here is also 4 meters. Okie dokie. Now what are we going to do? Well, first step, let's write some sum of the forces equations. If we do a sum of the forces in the x, set that equal to 0. We're going to have AX to the right. And I've drawn my tension going up and to the left because remember, ropes can only pull. So we have AX minus T. And it's T times the cosine of theta 2 because we want this component of the tension. Now if we look right here, both right now are question marks. So we're going to have to write another equation. So we'll come down here, we'll do a sum of the forces in the y direction. We'll say that that's equal to 0. That's going to get us AY minus 200 plus the y component of this tension here. Well, the y component of this tension is pretty much this component right here. Because that's opposite of the angle, we're going to have tension times the sine of theta 2. And right now, again, we don't know AY to start. We don't know the tension to start. So this is also unsolvable. Well, that leaves us with only one choice, which is to sum the moments. And we definitely want to sum the moments about point A this time, because if we did it about this point here or this point here, we might actually have to include two of these unknowns here. So you always want to do the moment about a point, in this case A, the pin, where there are two unknowns. So we do sum of the moments about A, set that equal to 0. AX and AY go through that point, so we disregard them. We have our 200 kilonewtons going counterclockwise times 4/3. So we're going to say negative 200 times 4/3. Clockwise, negative. Plus, now this is where things get a little interesting, because over here, the tension is almost, in my picture, looks like it's perpendicular to the beam, but not really. It's at some weird theta, so it's definitely not perpendicular to A yet. So what I'm going to actually do is I'm going to do like what we did in that crane problem. I'm going to use force vectors and line of action together. So what that means basically is, if I use this orange pen, over here we've got this 4-meter tall triangle. There is a distance in the x here and a distance in the y. Right here. Now what we know about this triangle here is that this triangle is actually theta 1. And we know theta 1 is equal to 60 degrees. So what we're going to do is we're going to take this tension, we're going to take the x component, and we're going to multiply it by dy. We're going to take the y component and multiply it by dx. And I'll show you how that looks in the equation. So we're going to have the tension y, which is going up, times dx plus 4. So we have plus ty times dx plus 4. And that's going to be a counterclockwise moment because this tension is trying to get everything to rotate counterclockwise. Then we're going to throw in the x component, which is going this way. That's also going to cause things to rotate counterclockwise, so it'll be positive, and it's only a distance dy. So I have plus tx times dy. And that's also counterclockwise. Now what we need to do is figure out what these actually are. So I kind of just draw some arrows here and kind of expand these terms out. So ty would be t sine of theta 2 times the distances, which to get dx, we can see that dx is equal to 4 cosine of 60. And dy is equal to 4 sine of 60. So we have t sine theta 2, which is ty, times dx, which is 4 cosine of 60, plus this 4 over here, because it's not only this component right here, but it also is this far away. So that's that over there. Now we can bring this down, draw a little bracket, squiggle, squiggly squigs, and we can now draw this. Tx is t cosine of theta 2, and then dy is 4 sine 60. Now we know theta 2 is 55 degrees, so you could plug that into your equation right here, and pretty much what you would get after a little bit of simplification is you would see that this is 266.66 repeating. Move that to the left side, so that would become positive. You get 266.66. It's going to be equal to, this component ends up being 4.915 t after you distribute these terms and multiply everything out. And this term over here ends up becoming 1.98 times the tension. So now we just have one variable, the tension. We can solve. We're feeling nice and happy. Woohoo! And what we get is that the tension is going to be equal to 38.63 kilonewtons. There we go. All done. Now we just need to go back to the beginning. So we'll take this, and we'll plug it in above. If this was our first step, and this was our second step, and this was our third step, we'll plug it back in above into equation 1 and equation 2. So when we take the tension's 38.63, we multiply that by the cosine of 55, what we find is that AX is equal to 22.16 kilonewtons. We take that and we plug it into some of the forces in the y. What we'll get is that AY is equal to 168.35 kilonewtons. And that's it. That's how you approach this distributed load problem. First step, always take the equivalent of the distributed load. Draw that in the correct position on your free-body diagram, and then just treat your problem like it's a regular 2D rigid body problem with some special inclines, things like that. But that's it. Sum the forces, find the equation with only one unknown, and then you solve.
There you go.
Okay, everyone, that's it for distributed loads. Hopefully, by looking at the real-world examples and all of the practice problems, you've got a good handle on the concept and are ready to move on to the next topic.
Of course you're going to be a star.